Let's get going with one of the most complex topic in the world of data science known as optimizers. We will cover this in two parts. This is the part 1. Let's start without any delay. So guys, grab a notebook and a pen and grab a coffee as well because I'm not going to see my watch while shooting this video, okay? This video is going to be long, informative and deep, okay? So let's start. You are going to understand what are basics of optimizers in machine learning and deep learning. Then you are going to understand the maths behind it. We are also going to understand some intuition behind the various optimizers. And then we are going to understand the Python implementation. Okay. So let's start, and we will start with the very basic. We will start with what is optimizer. If somebody asks you what is optimizer in machine learning and deep learning, okay? So let's start from here. So algorithm or method, okay? Optimizers are nothing but algorithm or method to adjust adjust parameters. Adjust what? Parameters of model, okay, parameters of model to do what? To minimize the loss function. Here I have written some keywords knowingly, and I want you to be absolutely clear on what are these keywords. I'll just highlight it, okay? Parameters, minimize and loss function. Very critical, these three things here, and let's be absolutely clear on what I mean by parameters first. What are parameters of a model? Parameters of a model, example of parameters of a model could be weights in neural network. Okay, weights in neural network. Or example of parameter of a model could be coefficient in linear regression. Okay, coefficient in regression, I will say. Okay. So to keep it very short and simple, the meaning of parameter is the values of your what you are trying to get, right? So values of your model definition, for example. So if I tell you what is your neural network, you can simply tell me this is my neural network by giving me weights and bias age values, right? If I tell you what is your linear regression model, you can simply tell me this is my linear regression model by giving your coefficients, right? So parameters of a models are nothing but what is that you are trying to obtain when you say that I am fitting a model. Okay. What is that you are trying to obtain when you say that I am learning the pattern? That becomes your parameter. Okay. Your final model. Now minimize, there is no confusion here. Minimize, maximize. Minimize means lowest value. What is the loss function? Let's try to understand with a simple example again. Let's say you have a simple data here where one column is temperature of the day and other column is, let's say, humidity. Okay, humidity percentage, something you can take. So temperature 21, 22, 23, humidity, let's say 10. I'm just giving some random numbers, 10, 11, 12. Okay, let's say this is your training data and your job is to predict humidity based on the temperature. You have to train a machine learning model. Okay, so this is your x independent variable, this is your y target variable. Okay, let me write it in different colors so that we don't confuse with some other things. This is your x and this is your y. Now suppose you trained this model and then you are trying to predict now, so this becomes your y hat. Okay, so predicted humidity from your model will be, let's say here in place of 10 your model says 15, in place of 11 your model says 21, in place of 12 it says 20. Okay, here the difference between your actual and predicted, the difference between your actual and predicted, the difference between your actual and predicted, which I can represent here as y minus y hat. Okay, this value, okay, y minus y hat will be here minus 5, here it will be minus 10, and here it will be minus 8. Okay, these values that you see here form your loss function. I'm not saying these individual values are values of your loss. I'm saying these values form your loss function. So When I say minimize the loss function, the meaning is very simple. Minimize these values. Bring it as close to zero as possible. Okay? If you have understood this, then can I simply say that loss function, loss function, okay, is a function of actual, actual and predicted values? Can I say that? You will agree with me, I can say that. Okay. If I am saying loss function is a function of actual and predicted, can I say loss function is a function of y and y hat? Right? In this definition, I'm saying y and y hat, right? So loss function, which is basically a function of y and y hat, and if you are fitting a linear regression model, this y hat is nothing but, some people will write here mx plus c, some people will write here beta naught plus beta 1x, and some people will write here basically h naught x plus h naught x. And to keep it very simple, I'll just write here x h naught x. There could be a h1 also. For example, I can say h1 x and h naught, or mx plus c, or beta 1x plus beta 0, whatever you call it. But to keep it simple, I'm removing that slope thing, okay, the constant thing I mean to say, and I'm keeping it h naught x. So h naught becomes your coefficient, h becomes your input value, actual input, this x, okay. Can I say this is this function h naught x? So basically, loss function is a function of actual and predicted. Loss function is a function of y and y hat. Loss function is a function of this constant. Now please pay attention here. Loss function is a function of this constant and this constant. X is a constant here. So what is variable here? The variable here is only one thing, that is your h naught, which means coefficient. So if you have to increase or decrease the value of loss function, what you need to change? You need to change this h naught, which means the coefficient. Okay. And hence it is being said here, need to minimize the loss function to adjust the parameter. The parameter is nothing but your coefficient. Okay. Hence I told you this is the definition of the parameter, coefficient of linear regression. An example. Okay. Let's move a step further now. You have understood that loss function can be of any form, this form, okay? On one x, this could be your loss. On this x, this could be your parameter. Loss function could be of this form. This is your loss, this is your parameter. What we want to do? We want to reach to the minimum of loss function, for example, here, and we want to capture this parameter value, for example, theta 1. We want to reach to lowest point in the loss function, for example here, and we have to capture the parameter value, for example theta 1. Okay, what we are trying to do, we are trying to minimize the loss by optimizing the parameter value. Okay, adjusting the parameter value. Now let's move one more step and let's try to see how we will optimize the parameter value. For optimizing the parameter value, we have to start from somewhere, right? So, for example, here suppose somebody asks you what is the optimal value of h naught. You don't know, but you need to start from somewhere, right? For example, if you start at one point in this curve, right? If you start at, let's say, 1 point here, 1 point here. Now, which direction you should move in? Okay, so I'll just draw xy plane one more time. Let's say on y-axis is your loss, on x-axis is your parameter. From this point, right, which direction you should move in? Either you should increase theta or you should decrease theta. That is the question at hand. Okay, and that is where optimizers come handy. So let's try to understand the answer of this question. But first, here it is defined in which direction you will move will be defined by two things. The first thing is direction, in which direction you need to move, and second and important thing is how much you want to move. Okay, how much you want to move. Now please pay attention here guys, very important here. Suppose this is my minimum point, okay, and there is here I have to reach because this is the global minima. So basically From calculus, you must be knowing this is kind of local minima and this is global minima. So our objective is to reach to, let's call this point A and let's call this point B. Our objective is to reach to point B. Okay. But for reaching there, you have to move in this direction, right? Let me take a different color. You have to move in this direction, right? So direction becomes really important. Okay. And how much you want to move in one shot or one attempt, right? Or one step, that is also important, because suppose if you come here, right, then you have to start moving slowly to reach here. If you move too fast, right, you will again start going in this direction. Okay. Direction is important and your step size is important. How much you want to move is important, and in which direction you want to move is important. Okay. So based on these two things, right, the value of theta is defined as theta is equal to theta minus alpha gradient of j theta. I will just explain you what is this in a moment. But imagine this is theta at point A. Okay, so I have defined 2 points A and B. Okay, so theta at point B will be theta at point A minus alpha times gradient of loss at point A. What is the meaning of gradient of loss function at point A? So here, in which direction you need to move, right? To determine that, you have to compute the gradient. Okay, gradient means you have to compute the derivative. So from the concept of calculus, right, if there is any curve, okay, for example, suppose this is a curve. At any point, if I compute the gradient, for example, let's say this is loss and this is theta. At any point, if I compute the gradient, right, it tells me that if if I increase theta, will the loss increase or will the loss decrease? Okay. So for example, let's say this is my point 1. Okay. And this is my point 2. I am taking gradient at 2 points. Okay. Point 1 tells me that if I decrease theta, then my loss will reduce. Whereas point 2 tells me that if I increase theta, then my loss will reduce. This is very important concept here, known as the concept of gradient. Okay. I have explained this in detail in one of the Unfold Data Science video. You can search for Unfold Data Science gradient descent. So I'll be referring to some videos here. You can simply search Unfold Data Science, say gradient descent in YouTube. Okay. So you will come to this video. I have explained in detail, but for now, this is very simple to understand. In calculus, at any point, if I want to reduce this curve, right, then the gradient will tell me which direction to move in. Okay, whether to increase theta or decrease theta. Okay, so that is this gradient term in the end that you see here, this term. Okay, and this term alpha is known as learning rate. And learning rate is important because learning rate tells you what should be your step size. So this tells you which direction you should move in, this thing. Okay, and this tells you how much aggressively or slowly you should move. And these two things combined give you the step size. Okay, so I will repeat one more time. Suppose I am trying to minimize this red curve here, this red curve I am talking about here. Okay, in this red curve I am at point A, but I want to reach to point B. Okay, what I need two things. One is direction, in which direction I should move. One is step size, because I told you the problem is if I move too fast, I may miss this point. Okay, if I move too slow, it may take a lot of time to reach to this point. Okay, what should happen? I should have a optimal step size. How to take that optimal step size is basically by combining two things. One is learning rate and other is the gradient direction. So you take the direction and you multiply with learning rate, and then from you will reach the theta b from theta a. For simplicity, if theta a value is, let's say, 0.8, okay, and this is the step size, right? So this comes at 0.2, then you will reach to 0.6. If this comes to plus, then you will reach to 0.10. Okay. So in this case, this becomes your point A, this becomes your point B, and this becomes your step size. Step size. Okay. There are three things here. One is how you want to move it, what is your step size. Okay. Now we have understood how the steps are taken and how the loss is minimized. Now what I'm going to do is I'm going to plug in the actual formula of a loss function and try to show you how gradient descent works. Okay, the gradient descent is the very first optimizer that we are learning here. So what I'm explaining you in this curve is basis of something known as gradient descent. Okay, gradient descent. But I will also explain you with mathematical formula now. So let me go here and try to write one more time how theta is updated. Okay, theta is equal to theta minus alpha times of gradient of loss. Correct? Why we are taking this? We want to move to the new theta from the old theta, and this is my step size. Okay. If this part is clear, now I will go into little more mathematical detail here. Can I say that the loss function for my linear regression is 1 by m? So I'm writing here mean squared error loss. Okay. Mean squared error loss. Please pay attention here. I is equal to 1 to m. Okay. H naught, which is my coefficient, I will multiply this with xi for every I. Okay. And I will take the difference from actual, fine, and I will just square it. So what I'm trying to do here is I'm trying to show you the same thing. The difference between actual and predicted, actual and predicted, actual and predicted. If you square all these things together and divide it by 3, right? For example, square of this is how much? 25. Square of this is how much? 100. Square of this is how much? 64. Okay. You take these three numbers, you sum these three numbers. Okay. And you just divide it by m, that is 3. Okay. Whatever value you get is basically the value of loss for this particular use case at this particular prediction. Okay. So what I'm trying to do here is I am trying to tell you that this is the generic loss function, mean squared error loss, one of the loss function. So in the beginning, I told you what we are trying to optimize loss using what parameters. So this is my loss. This H naught is my parameter. Now I will try to show you how gradient descent works. Okay. So I will just write here one more time so that we can refer it. This is basically loss or cost function. So I want you to comment me in comment section what is the difference between loss function and cost function. If you have confusion, there is an full data science video. You can just go and watch that as well. M is basically number of examples. Okay. H naught. H naught when you multiply with xi. This is nothing but prediction. Okay. And prediction is nothing but this one. So I will just a moment explain you what is this. So theta is nothing but coefficients. Okay. So here, if you see here, right, theta is the coefficient. So when you your model's coefficient basically, these coefficients is what we are trying to optimize. Okay. So this is basically your prediction that in simple words you can write like this also for 1 point, and this is basically your actuals. Okay. So this is very clear, very simple. This whole thing in red box is your loss function. Okay. And loss function is basically the summed square of your actual and predicted values. Now let's move ahead and try to see if this is my loss function, then how we will optimize it. Okay. So for optimizing it, as I was telling you, the formula that we have been chasing since beginning is theta is equal to theta minus alpha times of gradient of loss, right? This is what we have been chasing. Now, the gradient of loss with respect to what? The gradient of loss with respect to our parameters. So our parameter in this case will be what? Our parameters will be theta only, right? Because theta is what we are trying to optimize. So if you see here, right? H naught is basically, I'm trying to tell that this is my theta metric. Okay. So theta is basically, you will have multiple coefficients in your linear regression model, right? So those coefficients is what we are trying to optimize. Okay. So now this formula we will extend a bit. Suppose if somebody tells you to find out gradient of that loss function with respect to theta. So let me write here gradient of that loss function with respect to theta. So first of all, I will write this loss function. Okay. I will write this loss function. Okay. So this inside is my loss function. This is my loss function that I wrote before also. This is gradient with respect to theta because theta is what I want to optimize. Okay. Now this squared term, right, that you see here. Let us find out the derivative of this squared term. Derivative of squared term. Okay. And what we are going to do here, we are going to simply say theta t xi, okay, minus yi square. By the rule of partial differentiation, it is very simple to do this differentiation. Okay, minus yi multiplied by xi. And this one, when you plug in the above formula, right? When you take this differentiation, because 1 by m is a constant, so it will come out anyway. So if you plug it in the above formula, right, then derivative of theta with respect to j theta, right, that we are trying to find out, right, it will be 2 by m because m is anyway come out. I is equal to 1 to m. Okay. Theta t x I minus y I multiplied by xi. Very simple. So what we are doing, since 1 by m is constant, right? So it will come out and it will get multiplied with this 2. And then inside what remains is this. Okay. What remains is this. And if we have to simplify this, right, then we can simply say 2 by m. Okay. So now I will remove this summation. Reason being, I'm going to do this in Python now. Okay. X transpose x theta minus y. So this is simplified version of this. I will tell you how this is the simplified version of this. What I'm trying to do here is I'm trying to take transpose of x because that is what gets multiplied with the weights. Okay. And then I'm multiplying here x theta. X theta is nothing but my prediction. And this y, internal y is my actual value. So this is basically your derivative term. This is basically your derivative term. Now, this derivative is your function. This is a function of what? Here your x is constant, y is constant, this x is constant. So this becomes a function of theta. Now, this can be very well optimized for theta. Okay. So how we can do that is this part from here to here, right? You should not have any confusions. The reason being this same formula, right? Theta is getting multiplied with xi, getting subtracted with original, and then xi is here. So I am just simplifying. I am simplifying this multiplication using x transpose and x theta so that I can put in the Python formula. Okay. And now if I have to write this in Python, okay, what I'm going to write here, if I have to write here, I'm simply going to write here 2 into numpy dot product because I have to take a dot product. Okay. X numpy dot x weight, okay, x into weight minus y. I'm writing inside now. I'm writing this part now. X weight minus y, okay? And this whole thing divided by length of x. Because 2 I am taking in the beginning, m length of x I am taking in the end, okay? When I say np dot, that takes care of this part, okay? This x I'm writing, and then inside again I'm saying np dot x weight, that is this part, okay? And then the y. So this part, this complete part, right, takes care of my derivative term. So what should happen now? From the beginning we are changing this formula, right? Theta is equal to theta minus alpha, then derivative. So if I consider this entire thing as, let's say, Aman, okay, just an example, then what I need to write now in Python is theta new is equal to theta old minus learning rate times Aman. Okay. And based on this, it will give me the optimal value of theta. Let's try to do that in Python. And this entire thing that I explained you now is basically called a gradient descent. Okay. So the mathematical calculation I knowingly showed you. The reason being, you will understand how the mean squared error is getting optimized here. Okay. This is your mean squared error function. In this mean squared error function, if you differentiate with respect to theta, that is partial derivative here. Here what you will do, you will simply do a derivation and you will get this. Now in Python, I'm going to write the same thing and I'm going to show you how the weight is optimized. What what all things I will need in Python? I will need X independent variables. I will need Y target variables. I will need initial value of theta because as I told you somewhere I need to start initial value of theta, and I will need learning rate, okay? And I will need how many times I want to run the iteration. So that is nothing but epoch. Let's define these 5 things in Python and I'll show you how I can do the gradient descent without using any TensorFlow, Keras, etc. So here X I'm defining, Y I'm defining. As I told you, initial value of theta I need to define. This is my initial value of theta, which is 0, 0. Learning rate I need to define. This is my learning rate. Epochs I need to define. So this is my epoch. Okay. What I'm saying here, for epoch in range epochs, gradient is equal to 2 into np dot x weight minus y divided by len x. So this term is my gradient, as I was telling you. This term here is my gradient that I'm calling Aman here. Okay. That is my gradient. So next thing what I have to do, I have to do theta nu is equal to theta old minus eta times Aman. That's what I'm doing. Theta nu minus is equal to means it will take that value. Theta old learning rate into gradient. Same thing, okay? I will print weight and I am running 10 epochs. Let's run this. So as you can see here in the 10 epochs, right, it started from 0.3, then it went to 0.55, then it went to 0.7, then 0.9, then 1.11. Finally, it is going to 1.60, okay? Now, let us increase it to 100 epochs and see if it changes. In the end, what should happen is it should start stabilizing. I will tell you why. So if you see this curve, right, what will happen is if I want to reach to point B, right, what should happen is it should start moving in this direction, okay? And when it reaches towards B, right, then it should move slowly because I don't want it to miss this point also, okay? And when it moves slowly, right, then you will see the slow changes towards the end epoch. Okay, so that is what is happening. If you see here, initially the change is more. For example, it starts from 0.3, goes all the way till 1.8, 1.9, 1.9, and in the end, right, if you see 1.999999, same kind of values, right? So in the end, the movement is very slow and it is stabilizing at this value. Okay, so this is one. And if I make it 1000 epochs also, right, then you will see that it is stabilizing in the end. So now after a few epochs, there is no change at all, no change in the value, which means that my theta value is coming where it should come. And based on the epoch, it is taking the correct value. Okay. So initially it will be more movement, later it will be less movement. Okay. Why I explained you now, but let me explain you with another interesting uh, diagram here. Okay. So this is from Google developers. If you can see in gradient descent, right? I will not go into many detail, but as I was telling you on x-axis loss, y-axis value of weight. Starting point is here. Okay. Value of weight is here. This is negative gradient. This is negative gradient. This is loss and then next point. So from this point to this point, it's coming. Okay. Now let's go to the next learning rate and I will tell you how it is working. So this is very small learning rate takes forever to reach. So we should not give very small learning rate. Learning rate is eta in our case. Okay. In our case, learning rate is this eta. If you give very small learning rate, right? For example, 0.00001, right? What will happen is the step size will become very, very small and it will never be able to reach. I mean, if you see here, 1000 epochs also, it is not able to reach to the right number. So learning rate should not be very, very low. That is what it is saying. Learning rates decides your step size. So it should not be very, very low. And it should not be very high also. If it is very high, right, it will start overshooting your minima. Okay. So you should not make learning rate very high because that will make your, so optimal value is what we had put in the beginning. That is what is recommended for learning rate. Okay. You should have a good learning rate, that is 0.01. Now, if you go here, right, I will show you what happens with different learning rates. So here learning rate is 0.01. What happens in first step? Let's see. This is a loss on x-axis, sorry, y-axis, and value of weight is on x-axis. Okay. Let me step 1, 2. This is nothing but epochs. Okay. So if I'm pressing more, right, you will see that towards end epochs, right, it is becoming very, very slow. The reason is it is reaching to the global minima. And that is how it should happen. Okay. And after this, if I keep pressing, nothing will happen because it has reached the minimum. Okay. Now I will reset this and I will increase the learning rate to 0.4. What will happen is you will see that it will start taking a large steps now. Okay. So step 0, large, 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 large. But again, when it reaches there, it will be smaller because of the step size. Okay. Because of the gradient value basically. So step size is basically a combination of your learning rate plus gradient. That is what I am trying to tell you here. Your step size is a combination of learning rate and gradient. If your learning rate is large, but gradient is small, right? Then the small movement will happen. Okay. So if I make more, right, 0.20, I will reset and I will do in one shot only from here to here. After that here, after that here, after that here. Okay. So this model has reached the minimum loss. It is possible to achieve result with fewer steps. Okay. So depends on your learning rate and gradient. So in this chart, gradient is always in this gradient is telling to move in this direction. So it's moving in this direction. Okay. Now, if you make learning rate very high, what will happen is your function may never converge. So it will say that your function will not converge here. Okay. So it is going into altogether different direction. So 0.10 is the 0.1 is the optimal thing that you should try for. Okay. This is a recommended thing for normal plane gradient descent. This we are learning plane gradient descent. Okay. Not the other optimizers. Now, just keep in mind one thing, guys. In gradient descent, your new weight, your new red point here is basically a combination of previous red point adjusted with step size, and step size is decided by learning rate and gradient. Just remember this much. Okay. This is your very first basic optimizer known as gradient descent. Hence, I took a lot of time to explain this. There are two variants of gradient descent. One is known as stochastic gradient descent, and other is known as mini batch gradient descent. Okay, mini batch, I will say ZD. These two are different variants of gradient descent. Okay, stochastic gradient descent is basically when you say, when you send one sample of data in every iteration, one sample of data for weight updation. Okay, so what is the meaning of this is basically when you are updating your weight, right? Here, when you are updating your weight, what you are doing is, let's say in your data there are 500 examples in your training data. All these 500 examples will go to the network or wherever you are, whichever model you are using, and based on that you will optimize your weight. What happens in stochastic gradient descent is you will send the data 500 times. Okay, one sample will go once and weight will get updated, another sample will go once and weight will get updated. So suppose there are, let's say in your data there are, let's say 100 points, 100 data points, 100 data points. Okay, and 10 epochs. Epoch means one complete iteration of your data. Okay, so how many times your weight will update in gradient descent is 100 into 10, that is 1000 times. Okay, these many times your weight will get updated in gradient descent, stochastic gradient descent. Okay, in gradient descent only 10 times because you are sending 10 times only. In gradient descent you send the full batch, so you will send the 100 data points in one shot, hence only 10 times. Okay, in stochastic gradient descent you will send one data, so everything will run for 10 epochs, so 100 into 10 means 1000 times your weight will get updated. Okay, that is the difference. There are obviously some advantages and disadvantages that I want you to comment. And then mini batch gradient descent is something in between stochastic gradient descent and gradient descent. So gradient descent is full batch, stochastic is one observation, mini batch is basically n observation, n observation sent. Okay, so these are basically different flavors of gradient descent itself, so no need to worry much about it. The only difference is how much data you are sending in one shot. Okay, if you send everything, that becomes gradient descent. If you send one sample, that becomes stochastic. If you send n, that is between one and everything, that becomes mini batch. Okay, so these are different flavors of gradient descent. So now we will be moving to the another optimizer known as momentum. Okay, we'll be moving to another optimizer known as momentum. What happens as part of momentum is basically, uh, in momentum there is one slight addition on top of gradient descent basically. Okay, and that slight addition is basically concept of something known as velocity. Okay, so how the formula of momentum is, I will just write here and then I will explain you how it is different from velocity, normal gradient descent. So normal gradient descent, we update the weight theta is equal to theta alpha times j theta, right? This is what we have been doing. Okay, here in place of this what we will do is we will say theta is equal to theta minus velocity at time t. Okay, and velocity at time t will be beta times velocity at time t minus 1 plus alpha times j theta. Okay, now this is these two concepts we will understand. But before that, I will just explain you one simple concept that is known as exponential smoothing. Okay. So exponential smoothing is basically a simple concept that is used in the world of time series forecasting and signal processing and many other things. Okay. The concept is pretty simple. The concept is suppose temperature today is 21. Temperature tomorrow, let's say today is let's say 10. Temperature yesterday was let's say 20. Temperature day before yesterday was let's say 19. Temperature before that was let's say 16. Okay. So suppose if somebody wants to understand the temperature at T11, right? Okay, what should happen is the recent observation should be given more weightage. For example, the recent observation from T11 is T10. So T10 should be given more weightage. The recent observation from this is T9. T9 should be given higher weightage but lesser than T10, and so on and so forth. Okay. So suppose if I have to forecast the temperature tomorrow, that is T11, highest weightage will be given to temperature at 10, then 9, then 8, and then 7. Okay. How this is implemented in mathematics, I will just show you one very nice Medium article here. What it tells you is, if you write a formula like this for velocity, for example, velocity at time 1 is equal to velocity at v0. And whenever I say time 1, time 2, please do not confuse. The meaning of time 1 and time 2 is very simple. Okay. Time 1 is basically this time. Okay. And when I click one more time, that becomes T2. When I click one more time, that becomes T3. Okay. This is nothing but step. Okay. When you are moving, that step. Okay. So here the velocity term is initialized with 0 if you see. And first of all, courtesy to this article writer, I will just give a courtesy to this person for writing this lovely article. Okay. And then I'm going to see this. Okay. So here V0 is initialized with 0 value. In our case also in my note, right? If you go here, we will initialize with some 0 value, but the next value of V1 will be beta times V0 plus 1 minus beta times theta 1. Okay. So beta times previous value plus you can think alpha is 1 minus beta here, and theta is nothing but our loss function. Okay. If you see this carefully, right, you will see that at time 1, this is 1 minus beta of theta 1. At time 2, this is 1 minus beta theta 2 plus beta theta 1. At time 3, more weightage is given to theta 3 and theta 2, and less weightage is given to theta 1. So if you see here, why I'm saying less weightage is because beta is a decimal number, and if you square that, that number becomes even less. Okay. So less weight at V3, right? At step 3, in our example, this is step 3, for example. At step 3, more weightage is given to step 3 value, gradient value, step 2 gradient value, and less weightage is given to step 1 gradient value. Okay. If I move one more step further, more weightage is given to current gradient value. Previous to that is also good, but after that beta square and beta q will be less value. So the meaning is very simple here. The meaning is velocity tells you that in which direction I am moving, right? Let's keep moving in that direction only, and that gives a speed to your convergence. Okay. So how that will help you basically is, as I was telling you, that is basically smoothing. Okay. So if I take this chart, right, that we are trying to optimize there in our Google code, right? If we start from here and if you want to reach here, right? So the ideal way we should move is like this. Okay. But sometimes what can happen is you will start moving like this, and this movement is unnecessary. Okay. This movement should be reduced. So what should happen is this movement should be reduced, and this should be as low as possible. Why do you want to move in that direction? We only want to move downwards, and that too fast. Okay. So that is what momentum does to you. What momentum does is it tells you, hey, this is the velocity term that has been derived from the previous velocity and gradient. Okay. Now adjust your weight according to this velocity. And what it brings to your model is speed. So if your gradient descent takes more time for the convergence, your momentum will take less time for the convergence. Okay. And It why it will do so? Because it is depending on the speed. So if speed is more, it will reach to the optimal point faster. If I have to define this in Python, right, I will go here and I will start defining momentum. As I told you, we will need weight, we will need initial velocity, learning rate anyway we will need, and we will need momentum value, that is 0.9 here. If you see, I'm giving here a momentum value, right, beta, okay, and epoch. So what I'm saying is gradient, we already know this gradient concept, we already know. If you see here, the velocity term is new here. Okay, gradient is same that is there in plane gradient descent. Velocity is momentum into velocity plus learning rate into gradient. So this is basically momentum into previous velocity plus learning rate into gradient. Four terms here if you see. Okay, first term, let me write in a different color. First term, second term, third term, and fourth term. Okay, so beta first term is momentum multiplied by velocity, that is previous velocity. Third term is basically learning rate, and fourth term is basically your gradient, and gradient comes from here. Okay, and then weight is getting updated. So if you see here, the trained weight, I'm not printing weight here, I can print like previous example, and you will see that it converges very fast as compared to the previous one. Print weight. Okay, and if I take 1000 epochs, right, then you will see that in the after some epochs, right, it has started coming to 2, which is the optimal value. Okay, but in previous example it is still at 1.99. Maybe it will come to 2, but it will need more epochs maybe. But this is very fast. Okay, because of the speed that you have given through the momentum. So that is your second optimizer, momentum. How momentum is different from your stochastic gradient descent or normal gradient descent is momentum adds the concept of velocity. What velocity does? Velocity gives speed in the right direction. Okay, and then you reach. What concept it uses? Exponential moving average in the background, but the purpose is very simple: give the speed in the right direction. Okay, that is your momentum. The next one that we are going to understand here is known as Nesterov. Okay, Nesterov accelerated gradient. Accelerated gradient. This is another optimizer, the third optimizer. And this one is very simple as compared to momentum, very similar as compared to momentum, just a minor change from the momentum. Okay, so if you see momentum formula here, what we are trying to do, we are trying to take a velocity and we are trying to adjust the weight based on the velocity. What we will do in NAG, this is basically called as an NAG. What we will do in NAG is we will simply update this to something known as a look ahead weight. Okay, so what happens in momentum is two things get applied. If you see here, right, one thing is velocity. It is a combination of velocity and gradient. Two things are getting applied here. Learning rate is anyway there, but if I ask you what are the two things that is working here, one is velocity and one is gradient. Okay, so here velocity and gradient both will be applied. Velocity and gradient both will be applied, but one after another. One after another. Okay, so here what will happen is in momentum, right, your both velocity and gradient will be applied at the same time, because you are calculating the velocity and then just updating the weight. But here what the system tells is there is a concept of look ahead weight. Okay, look ahead weight. I will just tell you how this look ahead weight is working. But for that, I will just write once the formula here, look ahead term basically. Okay. So the formula for look ahead weight is theta look ahead previous theta plus beta of velocity t minus 1. So what I'm trying to do here is I'm trying to take the previous velocity and I'm trying to derive the look ahead weight. Okay. And then I am deriving velocity based on this look ahead weight. So for example, beta of t minus 1, this remains same as the previous one. Okay. Loss function theta of look ahead. Okay. And then theta is equal to theta minus vt. So if you compare this with the momentum formula, right, this is very, very similar to the momentum. Theta is adjusted using vt only. Okay. The previous formula is basically same, just that this weight is look ahead here and this weight is not look ahead here. Okay. So what we are telling to system here is in NAG, we are telling to system is don't do gradient and velocity both at one time. So if you see here, look ahead weight is computed based on previous velocity. See here carefully. Look ahead weight is computed on the basis of previous velocity. So we get a look ahead weight and then we take the gradient of the look ahead weight to derive the velocity. Okay. So what is happening here is velocity and gradient both are getting applied, but not at the same time, one after another. Okay. So this is velocity at t minus 1. Using this, we compute look ahead weight. And then from the look ahead weight, we take the gradient and then compute the velocity. And then we adjust this. What is the advantage here? The advantage is very simple here. In your momentum, right? Sometimes what may happen is there is a risk of that momentum uh, overshooting your minimum. Okay. And sometimes what may happen is the convergence also might not be that fast as compared to nag. So nag helps you in a situation, in those kind of situation where there is a risk of overshooting, there is a risk of slower convergence, there is a risk of getting, not reaching to the optimal minima. Okay. So nag is just one improvement over momentum. If somebody asks you in interview, just one improvement over momentum. In momentum, there is no concept of look ahead weight. In nag, there is the concept of look ahead weight. So we compute look ahead weight based on the previous velocity. From the previous velocity, we take the look ahead weight gradient and then take the velocity and then adjust the weight. Okay. So Python implementation wise, it will again be, let's see how it is. Simple only. See here nag, weight, velocity, learning rate, momentum, epochs. All these things we have already done. Okay. So for epochs in range epochs, right? For I in range, look ahead weight plus momentum into velocity. That is what I'm doing. Weight plus momentum into velocity. Gradient, it is the same that we have been seeing all this while. Okay. And then this is momentum into velocity, learning rate into gradient. Momentum into velocity, learning rate into gradient. Okay. So both these things together is coming. And then what we are doing here, gradient is computed on look ahead weight if you see. Okay. Gradient is computed on look ahead weight and then we are taking here and then we are adjusting the weight. Okay. So I will also say here print weight. Okay. So I will simply run this. And as you can see here, weight is getting optimized here. And trend weight in this case is minus 1.72. Depends on epoch and depend on many other things. But just to let you know, I mean, we can set the starting point here. Okay. And then it will start training. So this is how it is coming in the nag. Okay. So three things we have learned till now. I know it is getting very mathematical in nature. So I will just give a revision and I will hold the rest three things. I have three more things to cover. As you can see here, one is ADA grad, one is RMS prop, and then there is ADAM. Okay. These three are the most important which are used normally in deep learning, but I will hold that because I want to your comments on this video saying that You are liking this level of deep mathematics because everybody may not like it. Okay. But before that, I will just give you heads up of what all we have learned. Okay. What is algorithm? What is optimizer? Basically, algorithm method to optimize parameter based on loss. I explained you what is loss. I explained you in loss, you have to optimize the parameter. Then I gave you example of how loss is related to parameter, how you can move in the direction of minimizing the loss. For moving, you need direction and you need how much you want to move. These two things will come from learning rate and gradient. This gives your step size. Then you move from the current state to the next state. This is your generic formula. This is your mean squared error generic formula. When you plug in mean squared error generic formula, differentiate with respect to theta to get the direction, to get the gradient, you get this generic formula. We have put this generic formula in Python and we have tried to run gradient descent in Python. That we have done. After that, I told you there are two versions of gradient descent, stochastic and mini batch. Stochastic, you send one sample of data for weight updation. Mini batch, you send something between 1 to n. N being total number of observations. Sorry, yeah, one and total number of observations, whatever you call it. N is basically how much you are sending in the batch. Okay. So if there are 100 data points, 100 times your 100 into 10 times 10 epochs is there, 1000 times SGD will update your weight. Normal gradient descent 10 times only. Okay. And I showed you the example in Google Developer here how with the update of learning rate, your weights are getting updated. Okay. Try to understand what happens when we reduce, when we decrease, or when we increase. After that, I showed you another improvement on top of gradient descent known as momentum. Sometimes gradient descent convergence is slow, it takes a lot of time. So we need momentum just to speed it up in the right direction. And how we do that is using velocity. I explained you the concept of moving averages, using which we give more weightage to the current velocity and less weightage to the previous velocities. And that we achieve using this velocity formula. I explained you using this gentleman's example how more weightage is given to recent values and less weightage to the far values. Okay. So that way we have learned how the velocity is computed and how the weight is updated using velocity. After that, one very minor amendment on momentum, that is called as NAG, Nesterov accelerated gradient. What it does is it does not apply velocity and gradient at the same point, rather at two different points. And what it achieves by doing this is sometimes with normal momentum there is a risk of shooting the minima, and sometimes the NAG performs better than normal momentum. Okay. And how to NAG, how to do this in Python is here. Okay. So I will take a pause here and I will wait for your comment to say that you need part 2 of this video, where I will cover 3 more optimizers known as AdaGrad, RMS Prop, okay, and most important, Adam. Adam is the one which is being used most of the time in neural networks, okay? But you have to tell me you are interested in this level of details in the comment, and then I will create that video. Okay. Till then, please let me know in comment how did you like this video, and also tell me the differences between SGD and mini batch, what you know, and any questions that you have. I'll see you all in the next video. Wherever you are, stay safe and take care.